Hi there. Thanks again for joining us. This is Space Nuts. My name is Andrew Dunkley, and every week we talk astronomy and space science. And we answer audience questions in our alternative show, which happens, wherever you are. I mean, we release it on a Monday, but that doesn't mean you listen to it on a Monday. Coming up today, we've got a couple of nuclear explosive stories. SpaceX is involved in one of those, and the other story is about blowing things up with atomic weapons from space. Yes, highly guaranteed, very, very effective as well. But I think there's probably a reason not to. We'll look at all of that. We're also going to talk about where Earth's dust came from, quite a bit of it, which might come as a bit of a surprise. You just have to look under just about every bed and kitchen table in the world to find it, as much dust as there is in the world. But we'll see where that is headed. And our galaxy reaches out further than we thought, apparently. There's some interesting science behind that. We'll talk about it all on this edition of Space Nuts.
15 seconds. Guidance is internal. 10, 9. Ignition sequence start.
Space Nuts.
5, 4, 3, 2. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1.
Space Nuts.
Astronauts report it feels good.
And joining us again to talk about all of that and more is Professor Fred Watson, astronomer at large. Hello, Fred.
Hello, Andrew. Good to see you.
Good to see you
today.
too.
Yes, we sort of missed a few days, haven't we?
Yes, you've been off conferencing.
Yes. So the annual science meeting, as it's called, of the National Astronomy Society, the Astronomical Society of Australia. It's where all the professional astronomers get together and talk about what they've been doing, their research. It was a big meeting. There were, I would have guessed, maybe couple of hundred people there altogether. That's quite big for astronomers, and in a country that's only got 700 astronomers in it.
Yeah.
But what was interesting and what was very, I think, heartening for me was the number of youngsters that were there. I call them youngsters, people under 50. People, the new generation of astronomers, most of them whom I didn't know, and they've no idea who I am, and that's fine. That all was okay. It just contrasts with a few years ago. So when I was the astronomer in charge of the observatory at Coonabarabran, we were kind of the shopkeepers. So all these astronomers used to come through, stay in the lodge and do their research using the telescope. So I knew a large fraction of the astronomical population of Australia, but that's changed because my job, that job is no longer mine, and so I don't see people the same way. But it was very nice to meet a lot of new faces and catch up with some very old faces as well, some even older than mine. And we also discussed matters such as the future of Australian astronomy, because that's in a interesting state at the moment, with the government having declined to engage in membership with the European Southern Observatory. We are now working on Plan B, and it looks promising.
Yes, fingers crossed. There's a lot going on. Okay, we should probably get stuck into these stories because there's a lot to discuss. The first story is a double bunger about nuclear energy and atomic weapons. We'll start off with the story about SpaceX, and they're looking at nuclear power in space, nuclear-powered satellites. What's the story here?
It's a test launch, really, a launch of a CubeSat, basically, that has not a nuclear reactor inside, but basically a capsule of something called tritium, which is sometimes called heavy hydrogen. It's hydrogen with two neutrons in it, as well as the proton at its center. And it's radioactive. Tritium is, I suppose you'd call it mildly radioactive. We used to use tritium standard lamps at the observatory when I was working there, which was a little capsule of tritium with some phosphor on it, and basically the electrons released by the tritium lit up the phosphor and gave a very constant glow, so we could use it to calibrate other instruments. So I've been close up and personal with a little nuclear power source, a bit like that, but it was just making faint light. This one is one that's been developed by a private company, and it's basically a company called City Labs in the United States. They've built a little, as I said, it's effectively a CubeSat, which has this little nuclear, not nuclear reactor, but nuclear power source inside, a tritium source that I've just been talking about, which doesn't actually convert the electrons into light. It converts them directly into electricity. So they've got these panels on the side of it that take the electrons that come from the tritium and turn them straight into electricity. It's called Bohr, B-O-H-R, which is a bit of a play on words because Niels Bohr was one of the great founders of quantum theory. Same spelling. A Danish one, a Danish scientist. And it stands for beta voltaic. And a beta voltaic is taking the beta particles, which are otherwise known as electrons, turning them into electricity. So it's beta voltaic orbital high reliability spacecraft. That's where you get the BOHR from. And it's been launched. So SpaceX's part in this story is just to provide the taxi up into orbit. It's a transporter mission, one of SpaceX's taxi rides to get stuff up and down from or up to orbit, coming down to different story. And most of them just burn up. Yes, but it is probably the first CubeSat to include a nuclear power system, and maybe, just maybe, will sort of illuminate the way for a new generation of spacecraft which are equipped with these nuclear power sources.
I suppose they have to look at alternatives because we've been fairly reliant anyway, on solar energy in space, particularly with our orbiting satellites, but also with the International Space Station and others. But the time will come where we are in places where there won't be that much sunlight, and in some places there won't be any at all, and solar panels are going to be useless.
That's correct, and we've seen already the use of these RTGs, radio isotope thermoelectric generators, which are carried by both the Curiosity and the Perseverance rovers, as well as spacecraft in deep space like Voyager 1, Voyager 2, Pioneers, I think they've got them as well. And these are spacecraft that are so far from the sun that you get very little light from the sun in terms of using it to generate electricity. So they've had their nuclear power sources for a long time. They are quite different though from what we're talking about here. I think it's 13 kilograms, if I remember rightly, is the amount in a canister of plutonium dioxide, which is decaying all the time and getting very hot as it does that, and that heat is then used to generate electricity, and it actually dies away as time goes on. So these nuclear RTGs, the radioisotope thermoelectric generators, gradually lose their power, and that's why we hear from time to time, and we usually report this on Space Nuts, we hear of instruments on board Voyager 1 being turned off to save the power.
Yeah, and that happened again not so long ago, I think. But
that's correct. Yes, it did. There was one turned off quite recently. But perhaps more to the point, and what you've just said about there being some places that have no sunlight whatsoever, that applies to those deep craters near the moon's south pole, and that's where we're thinking of exploring. So it may be that these beta voltaic arrays or devices might well be the future of power generation near the moon's south pole, because you're in places where there's no light whatsoever from the sun.
That's absolutely true. Darn cold too, it is.
It is. It's always cold there, yes.
Indeed. That's a really interesting story, and we're obviously in the early phases of finding these alternatives. Is tritium safe?
It's probably something regarded, treated carefully.
Yeah.
It is generally safe. I mean, we never took any real precautions with the device that we had on the telescope, and maybe we should have done, although most of us are still around and in fairly good health. But yes, they are releasing electrons, beta radiation. It's if you had a high level though of tritium, if you had a significant amount of it, then you would have to be careful about how you handled it and where it was put, and if it needed shielding and things of that sort.
Yeah, so don't sprinkle it on your cornflakes or anything like that.
Yes, that's right. It's best to avoid it if you can.
Yeah. Sugar's damaging enough already.
It is. Tell my dentist about it.
If you'd like to read up on that story about the launch of the CubeSat with the tritium nuclear power device that they're testing, you can read about it at dailygalaxy.com. Let's keep on this theme, Fred, because that's the good news. The bad news is the problem of exploding nuclear devices in space or firing nuclear devices from space to targets on Earth. That's a real issue. I know, was it back in the 80s, the Star Wars push was all the rage in the news at the time, and that got shut down pretty quickly.
Star Wars was
that lasers?
A Reagan-era initiative. Yes, I think it was. Basically electromagnetic radiation to zap your satellites. It wasn't nuclear, though, because nuclear weapons in space are prohibited by the Outer Space Treaty of 1967.
So what's happening?
They're not allowed, but there may be some there launched by powers that stretch the envelope, if I can put it that way. Governments that stretch the envelope, and we don't know. We don't know if there are any. They're banned by the Outer Space Treaty, so there shouldn't be any nuclear weapons in space. But that's all very well. There's a lot of things that shouldn't happen, but that do happen, and so it may be that perhaps there are nuclear weapons in space. So the question is, how do you detect them if there are these weapons? And that's where this piece of research from the Massachusetts Institute of Technology has come from. It's a person whose name is Areg Danagulian. Sounds like an Armenian name, does that? Usually IAN on the end, Armenian. An associate professor of nuclear science and engineering at the Massachusetts Institute of Technology. And he has essentially thought of a neat way of building a device that you could fly in the vicinity of a satellite to detect whether it is carrying nuclear weapons. And it's all about the subatomic particles that nuclear weapons are all about. It's all about neutrons and the nuclei of atoms. That's where it all comes from. So what he has suggested, and I might quote from Dr. Danagulian's work. The risk is that if you did explode a nuclear weapon in low Earth orbit, then you basically wreck low Earth orbit for everybody. It's not the blast, it's just the subatomic particles that do it. And so what he goes on to say is this danger is compounded by the lack of a verification mechanism for the Outer Space Treaty. There's no detection methodologies that have been proposed in the scientific literature. So what he's saying is here's a concept and feasibility study for verifying a satellite's compliance to the Outer Space Treaty by observing the neutrons induced by spallation from the approximately giga-electron volt protons in the inner Van Allen radiation belts, which is a slightly complicated and technical way of saying you've already got subatomic particles in the radiation belts around our planet. If you can basically watch the way a satellite responds to those protons that are in the radiation belts. If, for example, that bombardment of protons from the radiation belts causes neutrons to be emitted, then you can have a fair degree of confidence that there might be a nuclear weapon on board, or a lot of nuclear fissile material, heavy elements like uranium. That's the kind of thing that this is all about. And so what this is all about is building a satellite that can detect neutrons coming from radioactive material. And he's basically suggesting a detector, what he calls an inspector satellite, that flies by the satellite that you're interested in, finding out whether it's got nuclear weapons. And it's got these detectors, which are almost like X-ray detectors, the kind of things that you see now in when you go for an X-ray, a chest X-ray. They're electronic. They're not photographic like they used to be back in the day. And they've got what are called neutron sensors. They're called scintillators. And you put those in a special arrangement with other detectors. And if you do that, then you can apparently sort out the neutrons from the other natural subatomic particles that are floating around near the radiation belts. And the neutrons come from radioactive material. And you can also see the direction that they're coming from. So you can sort of point this thing towards your target satellite, the one that you suspect might have nuclear weapons, and it will give you the direction of where it's coming from. And so just a quote from Dr. Danagulian. The calculations show that a 9-unit CubeSat-sized detection platform, that's something the size of, what's that, about 3 loaves of bread, something of that sort of size. It's quite small. It can identify a thermonuclear weapon from a distance of 4 kilometers in approximately 1 week of observation. Now, that's quite a long time. But apparently, if you could get it to within 1 kilometer, it would take you about an hour to detect a weapon. And that's promising. That's one flyby. That's, an hour of proximity. You could do that as you go past the suspect satellite. If you got an hour in close contact with it or close proximity to it within a kilometer, then you might well detect a nuclear weapon on board. And of course, you could improve that if you had more than one of these inspector satellites. If you multiplied them up, then you could get quite significant improvements in that performance. So it's really quite interesting. One quote that I really liked, and it's, I'm going to read from Universe Today, has a very nice article on this. The last sentence is, right now, nations like the USA and Russia rely on intelligence to know what the other is doing. And as we know from history, intelligence can get things wrong. You can fake intelligence, said Dr. Danagulian, but you can't fake physics. I like that. It's true. So you could do it by physics. Yeah.
They do mention in this particular article that there's one suspect satellite that seems to have been launched by Russia. And the bottom line is that it's been put in an orbit that is very strange and very hostile in terms of its radiation in that area. And the question is asked, well, it says, no one puts satellites there because it's highly radioactive. Why would you put a satellite in that orbit? So that's one they haven't identified as maybe carrying a nuclear weapon, but they've certainly identified it as suspicious.
Yes, that's correct. And so, highlighting that, I think, puts this article in context. It tells you that this is a real issue, and we kind of need to work on how you might detect nuclear weapons in space.
Of course, the other side of it is, if you do identify a satellite that's carrying a nuclear weapon, what do you do next? It's like trying to teach people not to overtake in merging lanes, isn't it?
Yes, but it's worse than that, really, because
a little bit.
We have nations that completely disregard international law. They invade other countries without so much as a a sniff of the all the international treaties. They just run amok among them, and away they go. And yes, so that's the possibility that we might already have them. There is a kind of corollary of this, which I was thinking of when I read this story, and that is that back in the 70s, gamma ray satellites were launched, satellites that detect gamma radiation, and that was to detect any in-atmosphere nuclear tests conducted on Earth, because there was a test ban treaty that was signed that all the signatories said, no, we won't test nuclear weapons in the atmosphere, but they had to verify it. And so the verification process involved a number of satellites being launched that could detect gamma rays, which would be emitted by a nuclear bomb being detonated in the atmosphere. Now, none were, but those satellites are what detected gamma ray bursts, these fascinating pulses of radiation that come from explosions deep in space.
Yeah, of course.
Not man-made explosions, but natural ones. Yes.
Because if they do start detecting nuclear weapons in space, then the parties involved, they won't say, "Oh, sorry, we'll take them all down." They'll find ways of hiding them.
Probably. Yes, that's probably right.
Gosh, it's tough, isn't it?
Tough world we live in.
Indeed, and beyond it in some respects. You can read that story at universetoday.com. This is Space Nuts with Andrew Dunkley and Professor Fred Watson. Let's take a short break from the show to tell you about our sponsor, NordVPN. Let's talk about your online security. Now, I can tell you from personal experience, last year when Judy and I were overseas, we ran into a bit of a frustrating issue. There were certain apps we simply couldn't use without a VPN connection, things like our banking apps. They wouldn't load, and even a sports app I rely on wouldn't let me watch games back home because of geofencing and things like that. So with NordVPN, I was able to watch football back home while crossing the Atlantic Ocean. It was pretty weird, but it worked. And NordVPN is the best in the business. With NordVPN, you can securely connect to servers all around the world, which means your apps think you're right back home, even when you're not. It also encrypts your internet traffic, hides your IP address, and keeps your personal data safe from hackers and trackers and anybody else who's trying to get at you online. And this can happen in public Wi-Fi situations, in hotels, airports, cafes, anywhere like that. The best part, it's fast. Thousands of servers globally, and their NordLynx technology allows you to run seamlessly. No slowing down. It is brilliant. Right now, you can grab the special Space Nuts deal through this URL, nordvpn.com/spacenuts. You'll get 4 extra months free plus a 30-day money-back guarantee. So there's absolutely no risk if you want to give it a go. That's nordvpn.com/spacenuts. Stay safe online with our sponsor, NordVPN.
Roger, you're loud and clear here also.
Space Nuts.
Our next story, Fred, is looking at all the dust on Earth and where it might have come from. Now, I was thinking cats because, they do shed, but it's a bit more involved than that. And what is really interesting about this story is they think a heck of a lot of it came from one source.
That's right, and it's a mysterious one as well. So this is quite a nice story from published in Science Advances. It's about the micro-meteorites that bombard the Earth. And it's a bit surprising. This stuff, we think of meteorites as being chunks of rock that come through the atmosphere. They have a blaze of glory and then land on the Earth somewhere. And what we've got there is a free sample of extraterrestrial material. But there are also these micrometeorites which rain on the Earth's atmosphere, and they're dust particles, as you've kind of hinted.
Yeah.
They're sort of always falling on Earth, and that is, again, it's a free gift from space. I think, so I was sort of vaguely involved with this stuff probably 50 years ago, back in the 70s. I think they were then called Brownlee particles. I
that
think
sounds
that's
familiar.
what we're talking about.
Yeah.
But they're now, I think, called cosmic spherules. I should check whether Brownlee particles and cosmic spherules are the same thing. But basically what they are is bits of meteor that have melted as they come down through the Earth's atmosphere, but they actually survive into the inner atmosphere, and they cool down and they form a little sphere because basically the surface tension of molten material brings them into a sphere, and that is the story so far, because that heating that they experience as the sort of parent body, the meteor or meteorite, as it comes through the atmosphere, it kind of destroys their chemical structure. The minerals in it get metamorphosed, they get changed because they've been subject to very high temperatures.
Yeah.
But there is a technique that allows you to look at some of the characteristics of these objects that is not destroyed by heat, and it's the oxygen isotope signature, which we've talked about before. We've talked about isotopes and how they, how we distinguish between heavy water and normal water and all of that sort of thing. It's basically the number of neutrons in an atom. So you've got these oxygen signatures that essentially let you group these cosmic spherules, the Brownlee particles, if that's what they are. And it turns out that so people do, they do population census statistics on these objects to find out what relationships they bear with one another. About 10% of them, of these spherules that have been identified and analysed, collect in a group that has got the wonderful name of Group 4, which presumably means there's another 3 as well. Yep. And it's what makes them stand out in this group is the oxygen isotope signature that I just mentioned before. It's depleted in an isotope called oxygen-16. But here's where the story gets very interesting, because no known meteorites have that same oxygen isotope signature. And you'd expect, if these things were common, that there would be meteorites that match them in their composition. And often with meteorites, we can get an idea where they've come from. Most of them come from the asteroid belt, from collisions between asteroids. That is a bit mysterious, that we've got these these small spherules of material that have come down through the atmosphere and got that globular shape. It's mysterious that we don't see any meteorites that match their composition.
Weird.
It is weird, yes. And so what they're suggesting is that it's basically something that comes from an asteroid whose characteristics are unusual, that we have not yet identified it.
Wow. Okay. So we're still looking.
We're still looking. There's a sort of sub-mystery as well, because a detailed analysis of this, you can break that group 4 stuff down into other smaller groups, and some of them basically show signs of having had 2 different minerals in them before they entered the Earth's atmosphere. One would be typical of well-known types of asteroids, and the other, as I said, doesn't correspond to any kind of known group of cosmic spherules or meteorites. And it's really quite remarkable that we're being bombarded by dust particles that come from somewhere which we haven't identified.
Yeah, wow. Could that mean they're from beyond our system, or it's just a part of the system that we...
I think it's...
I don't know what to think.
Yeah, I think it's the other way around, because the team who've done the research on this, a very, very thorough piece of research, they've basically, as you've used simulations, computer simulations, to essentially work out what conditions these things formed in when they melted coming through the Earth's atmosphere. And it suggested that the best fit they get to what they see, the sort of textures that are in the material, fit with relatively low velocities, 14 to 17 kilometers per second, which is pretty speedy when you think of it on Earth, but in space that's a fairly modest speed for a meteorite. That typically will be more like 30 kilometers per second. And so that low value suggests that possibly those particles originated in near-Earth asteroids, ones that are following a similar path through space to the Earth. And that might mean that we've got some sort of, in the Earth's environment, some sort of unusual asteroid that is not matched by all the ones that we know already.
Wow, that'd be something. That's probably going to be hard to track down, though.
Yes, that's probably right, and especially since it might not exist anymore. It may have collided and formed little bits that have basically rained down on the Earth.
Yeah. No, it wasn't Thea, Rusty.
No, it wasn't Thea, that's right. Yeah, thanks, Rusty. It's not Thea.
For the record, Brownlee particles and cosmic spherules are closely related, but they are not exactly the same thing.
Okay.
They represent two different stages or types of micro-meteorites.
There you go. Thank you for checking that. Yes.
That's all right. Yeah, they're very close, but they're not the same.
So I was on the right track.
You were. Yeah. Yes. And you can read all about that at the Daily Galaxy website. And the article was published where, Fred? I've lost it. Science Advances.
Yes, Science Advances, that's right.
Yes. I want to read the whole thing before bed so you sleep well.
Yep.
Yeah. This is Space Nuts with Andrew Dunkley and Professor Fred Watson.
We choose to go to the moon in this decade and do the other things. Not because they are easy, but because they are hard.
Space Nuts.
Our final story today takes us to the edge of our galaxy. Well, it takes us from the center of our galaxy right out to the edge of our galaxy, because we're talking about the whole thing, lock, stock and barrel. And it appears, Fred, with some very clever scientific brains in action, that our galaxy stretches out further than we thought.
It does. It looks as though the spiral arms are longer than we thought they were. And I think this is a very nice piece of work, as I hinted before, partly because it uses a technique that I think is really extraordinary. It's a very powerful technique using what we call light echoes. So the story, basically, to set this in context, it's very hard for us to produce a map of what our own galaxy looks like. And that's because we're embedded in one of the spiral arms. The stars that we see when we look at the Milky Way, they're stars that are fellow travelers in the spiral arms with our sun and solar system. But they only go out to 1,000 light years or so, because the spiral arms are so dusty that you can't really penetrate much beyond that. And if you were relying only on visible light, it would be like trying to draw a map of the whole of Dubbo from standing outside Dubbo jail there on, forgotten, is that Macquarie Street?
Macquarie Street, yeah.
Yes.
Oh, for the record, they're putting they've taken down the public building in front of the old Dubbo jail.
Which
is
there you go.
Now a tourist attraction, and they're turning it into a public common.
I like that idea. That's
It's
good.
going to look very nice when it's done.
So that would improve your view of the city of Dubbo, but it still would not let you make a map of Dubbo from just there. And that's how we are in our galaxy. If you're relying on visible light observations, all you're seeing when you look is the neighbourhood of our spiral arm, a local spiral arm. You don't get any hint or inclination of the structure of the galaxy beyond that. And in particular, if we see 1,000 light years or so, there's another 100,000 that we're not seeing because that's about the diameter of our galaxy. So the situation improves when you use infrared radiation. You can sort of penetrate through the dust and see actually towards the center of our galaxy. That's how we know about the black hole in the center of our galaxy, because we could see stars orbiting around it. But it improves even more on a broader scale if you can use radio telescopes, because you can plot where the clouds of hydrogen gas, called hydrogen, which radiates in radio waves with a wavelength of 21 centimeters, that you can plot out. But if you're going to try and draw a map, you do need to do some modelling with that. You've got to assume things about the rotation of the galaxy. So it doesn't just give you a direct map. And that could be wrong. We could have that little bit of it wrong, the stuff that comes from the radio observations. So what's happened now is it's a team, I think they're based in Italy, and what they've done is used a direct method of kind of setting up a standard ruler, because if you've got a standard ruler and you can see it in deep space, then you know how far away it is, because you can measure how long it appears to be, and if you know how long it is, which is what a standard ruler is, then you know how far away it is, and that's what they're doing. They have, and it goes back to something we mentioned earlier in the show, gamma ray bursts, these bursts of gamma radiation. Those bursts don't just directly come to us. They also bounce off or are reflected by clouds of dust in our spiral arms. And so by timing how long it takes for these echoes, as they're called, light echoes, even though it's gamma radiation, to what the delay is between a light echo and the source itself, which is the gamma ray burst. I should say they probably come from collapsing massive stars or merger of neutron stars, very energetic events because they're bright in gamma radiation. But if you look at a light echo from a gamma ray burst, it gives you a scale to this. You know how far. Basically, it gives you a standard ruler because you can time it accurately. You know that 300,000 kilometers per second is the speed of gamma rays through space. And if you know how far away it's gone in that time, then that gives you a distance measure. So you've got a standard ruler. It's a very, very nice way of doing this. And using that, these scientists... as I said, at least the lead author is certainly in Italy at ENAF in Milano. They've done this work looking at these gamma ray bursts with their light echoes, and that allows them to calculate basically the size of our spiral arms without relying on any kind of modelling. And so they think that the new observations indicate that our spiral arms are something like 10% longer than we thought they were.
Wow, that's a lot.
Yes, that's significant, isn't it? It's really, this is, as I said, this is very nice astronomy.
It is indeed, yeah. Of course, as you say, we can't really look at our galaxy. We don't know exactly what it looks like. There's a lot of science that they've put together to try and create the image of it. And even in this particular story, which is in theuniversetoday.com, they've got an artist's impression of what this new look is like.
Yes, that's all you can do.
Reminds me of an upside-down snail.
It does, yes, that's right.
A bit.
I see what you mean, yes.
Yeah,
yes, it's very helical.
Or a squid. Could be a squid.
Could be a squid.
Yeah. But in real terms, we just have to, it's a very, very well-educated guess, I suppose.
Yes, it is. It's a measurement. So you're right. It's an artist's impression. That's really the only way we can depict the Milky Way. Some of the depictions are very, very good, and they rely on the very best radio and infrared observations that have been made. But this is going to modify it a little bit by our new knowledge of the spiral arms. And I should say, it's the Chandra satellite, which is an X-ray observatory operated by NASA that has been used to make the measurements. And I do like the headline on a little NASA video that there is here, which is NASA's Chandra examines Milky Way at arm's length.
Yeah. Nicely done. Very well done. Clever with words.
Yeah, they are. There's some good people there.
So the article's in Universe Today, but you can read it in a deeper form through the NASA website, or the Astronomy and Astrophysics Journal, I think, has published the full paper, which is, it's
that's
got lots
the
of
European
numbers,
Journal.
Lots of numbers in it. Yeah, lots and lots of numbers. Numbers that are too big for my brain. All right. That's where we end the show. Fred, thank you very much.
Oh, a pleasure. As you said at the beginning, some nice stories there.
Yeah,
and,
some
very
great
glad
stuff.
to be able to share them with you.
Indeed. We'll catch you real soon. Thank you, Fred.
No worries. Thanks, Andrew.
Professor Fred Watson, astronomer at large. And as I say, between episodes, visit our website, spacenutspodcast.com or spacenuts.io if you're a lazy typist. And you can have a look around, visit our shop, sign up for the Astronomy Daily feed, send us some questions or comments through the Ask Me Anything button at the top, AMA. You might want to become a supporter. You can do that too. And don't forget to leave reviews of Space Nuts at your favourite podcasting platform. And thanks to Hugh in the studio, because he didn't turn up today. And from me, Andrew Dunkley, thanks for your company. We'll catch you on the next episode of Space Nuts. Bye-bye.
Space Nuts. You've been listening to the Space Nuts podcast.
Mission complete, Houston.
Available at Apple Podcasts, Spotify, iHeartRadio, or your favourite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.